So this question contains a graph. So first thing is an Oizerga analysis. The origin, if we look carefully, we could see that the origin is actually, that's where the 0 point would be. So on the coordinate system, we have our graph is actually located here. Doesn't go all the way back to the origin, which might or might not be a big deal. Y-axis is force. X-axis is time. So the things we can read off this graph are force and time. The slope is delta F over delta T. So that's the rate of change in force. And the area is F delta T, which is the impulse, which happens to be equal to the change in momentum. So we see we've got no net force, and it's applied almost like a push or a pulse very quickly, like so, like it's being patted or just shoved a little bit. So we're given, now it's in the scenario, a cart of 1 kilogram. It's traveling along a horizontal frictionless surface. A net force is applied to the cart. Could be in any direction. It's not saying. Initial and final direction of the cart and the direction of net force are unknown. So there's no directions known to anything. So the distance of one grid unit represents a change in velocity of 1 meters per second. And that's down here. 1 grid equals 1 meter per second. Which diagrams could represent the direction and relative magnitude of the velocity of the cart before and after the force is applied? Select 2 answers. 2. So let's look at the scenarios they've given us. Let's see. In this first scenario, if this is before and this is afterward, then the force must have been applied in that direction. Now the velocity began with -1 and ended up with +3. So the question we might first ask is if a force in that direction would cause this, and it would. Now, in this scenario beforehand, and this is after, we have a force being applied again in the same direction. And our initial velocity is -1, and our final velocity is +1. So this one is a delta V equal to 4, and this one is a delta V equal to 2. Because a delta V is V minus V0, and the instantaneous velocity, let's say, is 1, and initially was -1, so 1 minus a -1 is 2. And similarly over here, final velocity is 3 minus a -1, that gives us a change in velocity of 4. So understanding this the third choice, it's at rest, and for this to have occurred, again, the force is applied in that direction. And this is a velocity equal to 0, and afterward we have a velocity equal to 3. So our delta V is V minus V0. Final is 3 minus 0, so the delta V is 3. So we're comparing these. We have a delta V of 4, a delta V of 2, a delta V of 3. And lastly, when we look at this one, we have a V0 of +1. And for this to have occurred, again, the force is to the right. And afterward, we have a +5. So delta V is V plus V0. Final velocity is 5. Our initial velocity was 1. Delta V is V minus V0, excuse me, is V minus V0, and our final velocity is 5, and our initial velocity is 1, so that gives us a delta V equal to 4. Now, right off the bat, it should stick out to us that this one and this one give the same answer. If we're looking at 2 choices, that might be an indicator that those are the 2 correct choices. They all show positive delta V's. So what size is the proper delta V? Well, what we know the change in momentum, and the change in momentum is m delta V. Now the mass, we are told, is 1 kilogram. And So we need to find our delta V, and we can find our delta P through the area. Now the area, which looks like it's this triangle, and then there's this part over here, well, we can reflect that around the function and see that this is the area of a rectangle with a side of 1 and a height of 4. So we have a delta P equal to 4. Well, if delta P is 4, the mass is 1, then delta V must be 4. And that's what we see in these two blue choices. And that's why those are our two answers. We can get at this pretty quickly by just studying the graphs and looking for similarity, and we could dig down to the next level to really show it that that's really the answer of change in momentum before.